Hey everyone, my name is Krish Vijay and welcome back to KrishOnomics. Today I'm going to be talking about ARDL. You've probably heard of this quite often if you're dealing with time series data or just econometrics in general. You'll probably find it mentioned in tons of empirical papers online. But here's where it gets a little tricky. You might see papers that say they use ARDL, but what they really mean is they use the ARDL Bounds Testing approach. Now, I need to make this super clear. ARDL and the ARDL bounds testing approach are related, but they are absolutely not the same thing. ARDL is a model, but ARDL bound testing approach is, well, an approach. Yep. ARDL bounds testing approach is the method or the test we apply to the ARDL model. Remember that. For today, our focus is squarely on the model and not the bounds testing approach. Let's first see what ARDL actually stands for. It's the Autoregressive Distributed Lag model. And right there in the name, you get its two main components. The first is the autoregressive part, and the second is the distributed lag part. So, what exactly is the autoregressive part? Well, auto means self in Greek, and regressive means, regressing. So, it simply means that the current value of a variable is explained by its own past values. In an equation, it looks something like this. Here, y sub t is our variable at current period or period t. But notice there is another y variable on your right. It is slightly different. There's a t minus 1 subscript attached to it. That y sub t minus 1 means it is the value of y from one period before or the previous period. That's the autoregressive part. Now, this particular equation is usually referred to as an AR1 model or autoregressive of order 1 because there's only one lag dependent variable. But let's say we had more lags, say y sub t minus 2, then it will be an AR2 model and so on. Now, here's an example of how this autoregressive concept might look like in real life. Think of it like this. If you are trying to predict today's temperature, and one of the best predictors is often yesterday's temperature or the temperature from the day before. It's about using the past of the same variable to explain its present. So, if we have let y be the temperature, and we have daily temperatures from the 18th of June up to the 24th of June. Now, if our current period t is the 24th of June, then y sub t would be 27 degrees Celsius. And y sub t minus 1 is actually the day before the 23rd of June, which was 28 degrees Celsius. Going back further, y sub t minus 2 is 26.5 degrees Celsius, which was the temperature on the 22nd of June. Now, let's move on to the distributed lag part. This component is about how changes in one variable affect another variable over time. The lag refers to the past values, and the distributed means that the effect isn't just immediate, it's spread out or distributed across several past periods. In an equation, a simple distributed lag model might look like this. Here, y sub t is our dependent variable, and x sub t minus 1 are the current and past values of our explanatory variable. The coefficients beta 0, beta 1 tell us the impact of x at different time lags. The lag order of this model would be 1 because we are going back one period for x. We could easily make this a lag order of 2 by including an additional x sub t minus 2 to the model. Now, here's an example of how this distributed lag concept might look like in real life. For example, let's say you're looking at how advertising expenditure affects sales. It's not just today's advert that boosts sales today. An advert run last month or even 2 months ago might still be having an effect. That effect is distributed over time. So, let's assume Y represents sales and X represents advertising expenditure. And we are using monthly data from January 2025 to June 2025. Now, if our current period T is June 2025, Then Y sub T would be the sales for June, which is $70,000. And X sub T will be the advertising expenditure for June, which is $14,000. But for the distributed lag, we also care about past advertising. So X sub T minus 1 would be the advertising expenditure from May, which was $16,000. And if we included it, X sub T minus 2 would be the advertising expenditure from April at $13,000. This demonstrates how current sales are influenced by both current and past advertising efforts. So, if you put these two concepts together, you get the autoregressive distributed lag or ARDL model. It's a dynamic model that explains the current value of a dependent variable using both its own past values and the current and past values of one or more independent variables. This is an ARDL 1-1 model, which means we are using one lag of y and one lag of x plus current x. Understanding the ARDL model itself is the fundamental first step. In future videos, we'll dive deeper into how we actually use this powerful model, including crucial aspects like determining the right number of lags, understanding its flexibility, and of course, the ARDL bounds testing approach to uncover long-run relationships between variables. If you found this explanation helpful, please give this video a like, share with your mates who are also tackling econometrics, and subscribe to KrishOnomics.